Okay, I already know writing like this is going to be a nightmare, but we will try anyways. B, problem 1. Okay, this is kind of a long problem. Ms. Jones is pouring orange juice into 4 identical glasses for her 4 sons. She fills the first 3 glasses completely bronze out of juice when the 4th glass only a third full. Okay, what fraction of a glass must Mrs. Jones pour from each of the first 2 glasses into the 4th glass? These are all 4 glasses will have the same amount of juice, so the amount of juice at first is 3 plus 1/3. So 3 plus 1/3. I'm surprised I can actually write. I thought it would be way worse. I can kind of write. 3 plus 1/3. And we have to divide this by 4 because we want it to be equal. So 3 plus 1/3 is 10/3 over 4 is 10/12. 10/12 is 5/6. And then we do 1 minus 5/6 to get the amount that we have to pour out of 1 glass to get 5/6 of a glass. So we have 1/6, which is D. Or I mean not D, C. 1/6 is C. What can we do here? We have pages, okay. That's useful. So we'll probably just make each of these a separate page. Okay, problem 2. Carlos went to a sports store to buy running shoes. Running shoes were on sale. Prices reduced by 20% on every pair of shoes, so they became 0.8 times whatever. Carlos knew that he had to pay 7.5% sales tax on the discounted price. He had $43. Okay, so what is the original price before discount? So it has to be 0.8 times. This will be annoying. It's kind of annoying to write this number. But 0.8 times the sales tax increase, which is 7.5%, so it's 1.075 times x equals 43. And we want to solve for x. Okay. These two do not look like very nice numbers, but I guess I'll just calculate it like this. This times 8. So there's a 4 here. And then 8 times 7 is 56 plus 4 is 60. So you carry the 6 and put down the 0. 8 times 0 is 0 plus 6 is 6. And then you get 8. So 8600, and then we have 4 decimal places, so we go all the way to 8.6. Actually, no, we go all the way to 0.86. So 0.86 x equals 43. Oh, okay, and then 43 is 1/2 of 86, so this should just be 100 divided by 2, which is 50. So I think we're getting B. I should label these 1 and 2. This is 2. Next. 3, 4, 5. This is problem 3. 3, 4, 5 right triangles inscribed in a circle A and a 5, 12, 13 right triangles inscribed in circle B. What is the ratio of the area of circle A to the area of circle B? So I guess we'll just draw what they're saying. 3, 4, 5. And then some circle. I don't know how to draw a circle with this keyboard, but let's just imagine this is like a circle. This is not a circle at all, but you know. What is the ratio of the area? Okay, let me draw the other one too, I guess. 5, 12, 13. And these are right triangles, so these are where the right angles are. 5, 12, 13, and we have a circle here. I cannot draw circles without a proper pencil or something, but okay. And we just want to find the ratio of the areas of the circle, so isn't that just the ratio of the, same as the ratio of the diameter squared, so 5 squared over 13 squared is 25 over 169, which is a D. Okay. Okay, my trackpad froze up there for just a second, but I think it's back. Okay, my trackpad froze up there for just a second, but I think it's back. So, on to problem 4. Jackson's paintbrush makes a narrow strip with a width of 6.5 millimeters. Jackson has enough paint to make a strip 25 meters long. How many square centimeters of paper could Jackson cover with paint? Okay, well, it's optimal for him to just like slide it across, because if he does anything like a circle or anything weird, then like I don't think it's optimal really, because he would be like overlapping his brush strokes, so he would be double painting some things. But if he just slides the brush across into like a rectangle, then that seems pretty optimal to me. I don't think you can do better than that. So is it just a multiplication then? Like 6.5 millimeters and 25 meters, and we want square centimeters, so we have to convert each of these. You have to convert the width and the length into centimeters. So 6.5 millimeters is 0.65 centimeters. And 25 meters is 2,500 centimeters. So you multiply these two, so it's 65 times 25, because you can move these two and get rid of these two, right? So 65 times 25, which is 1625. Everything else looks like it's out of, it's like it's misplaced in terms of the order, of in terms of the powers of 10, so 1625 should be it. C. This is number 4, I think. Okay. Next. You're playing a game. A 2x1 rectangle covers 2 adjacent squares of a grid of 3x3 squares, but you're not told which 2 squares are covered. So you have 3x3 grid here. You have some grid here, and you have a 2x1 rectangle that covers 2 adjacent squares, but you aren't told, so it's horizontal or vertical, but you aren't told which 2 squares are covered. Your goal is to find at least 1 square that is covered by the rectangle. A turn consists of you guessing a square after which you are told whether that square is covered by the hidden rectangle. What is the minimum number of turns you need to ensure? Okay, you just want to hit this rectangle in the minimum number of turns, so, and you don't know where the rectangle is. So, okay, if you have like, you know, rectangles that look like this. I'm just drawing some possible rectangles to kind of visualize what the problem setup would be like. Okay, so for example, for the corner, like the good thing about a 3x3 square like this is that there's a lot of symmetry. So if you look at the corner, like top left corner, right? If you look at the top left corner, then kind of like there will be symmetry with like the bottom right corner, like, and probably even the rest of the corners, because everything's pretty symmetric. So if you analyze this, then there are like 2 rectangles that it hits if you do that. So there are 2 possible rectangles that this would hit if you guess this one. But if you guess, for example, one of these squares, like this, or this, which are also kind of like symmetric across, then there would be 3 hitting it, like the 3 in green. There would be, I can do it in red as well, I guess. This one, and this one, and all of these would hit this. So I think, okay, we can definitely do 4 if we just guess these 4, right? Then, because if you guess 4, then there's no way to select 2 adjacent squares on, there's no way to select 2 adjacent squares on the 3x3 grid such that you wouldn't have hit them, because this covers like everything. So we can definitely do 4, but can we do 3? So if we did 3, right, then we could do 3 in one line like this. So I guess I'll just do dots because it's easier to draw. You do this, this, and this for any of the rows or any of the columns, right? So you'd also do this, this, and this. But obviously these won't work because you won't be able to get coverage all the way across into the other rows and columns. And then maybe you could do something like you disperse the 3 here, right? Or something like this. But again, dispersion won't work because you have 2, for example, that you could put here, right? Or 2 that you could put here, and then that won't work. Actually, this should go here. 2 that you put here. So dispersion won't work. And then if you have something where it's kind of 2 in the same row or same column, but you put the third one in a different one, then even that won't work because you have an uncovered row or column that you could select from, like this. So I think 4 is the best that you can do. So C. What problem number was this? This was 5. We aren't doing too bad on time so far. Let's apply 6. Okay, when the roots of the polynomial are removed from the number line, what remains is the union of 11 disjoint open intervals. So what they're saying is you have a number line like this, right? And then you have these are the roots, by the way. So 1, 2, 3, all the way up to 10. And you're moving them from the number line, so I'm drawing them as open circles. And saying when you remove them from the number line, then what you have is a union of 11 disjoint intervals. So I'll draw them like this. This is 1, this is 2, this is 3, and then this would be like the 10th one, because the patterns are like the second interval is before 2, the third interval is before 3, so the 10th interval is before 10, and the 11th one is this one over here up to infinity. So I think, okay, yeah, those are the 11 disjoint intervals that it's talking about. On which of these intervals is, on how many of these intervals is p of x positive? So, okay, so I think what we have to do is we have to look at the graph. We have to imagine the graph of p of x, because if you look at the graph of p of x, then when it's above the x-axis, then that's when it's positive, and when it's below the x-axis, that's when it's negative. Like, because the y value dictates the value of the function when you graph it. And we know the root multiplicity, so that tells us whether when you hit the when you get the intercept, whether it's going to pass through the intercept, or whether it's because the intercepts are at the roots. So when you look at the roots, then you can tell whether it's going to pass, or when you look at the multiplicities of the roots, you can tell whether it's going to pass through the intercept there, or it's going to bounce off. It will pass through, I think, if the multiplicity is odd, and it will bounce off when the multiplicity is even. Yeah, because like if you have y equals x squared, then it's like a parabola, it bounces off that origin right there. So I think that's the pattern, if I remember correctly. And the only problem is we need to know whether it's positive or negative to start, and whether it's positive or negative to finish out. Or like it only matters to start on it, like to start. Because at the end, when it finishes out, it's just going to bounce off, because it's at the multiplicity is 10, so it's going to bounce off, and it's going to continue in whatever side of the x-axis that it is. So when we start out, what happens? When we start out, then you can think of that as like negative infinity, and I guess the only way to tell is to look at the degree of the polynomial. So the degree of the polynomial is the sum of the numbers 1 through 10, so we know that's 10 times 11 over 2, which is 55. So, which is odd, so we know this is going to be like an odd degree polynomial, so that means that it will start out as negative. So I guess I'll just draw them all out to see. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm just gonna call this 10. And then imagine it kind of continued here, right? So you start below and then you pass through, right? And then because you're at 2 and it's even, you bounce off because the multiplicity is 2, and then you pass through 3 and then you bounce off 4, and then you pass through 5 and you bounce off 6. And you keep doing this M-shaped thing, right? And then eventually when you bounce off 10, you gotta keep going, whatever the shape is there. But okay, so let's look. This is positive 1, 2, 3, 4, 5, 6. So I think it's a D. Okay, number 7. For how many integers n does the expression square root of log n squared minus log n completely squared over log n minus 3 represent a real number where log denotes the base 10 logarithm? So, okay, log of n squared is the same as 2 log n, so everything can be written in terms of log n, so I'll just let log n equal x. I'll just write log as lg to save some writing. lgn, which is log n equals x, right? So we can just think of this as square root of 2x. Writing is such a pain. Square root of 2x minus x squared over x minus 3. And we want this to be greater than or equal to 0. Like the inside has to be greater than or equal to 0 in order to make this work. And we know x is a logarithm, so x itself has to be greater than or equal to 0 as well. Because the logarithms can't be negative, but they can be 0 if n is 1 basically. So x is greater than or equal to 0 is a required thing that we have to keep in mind. And I guess we have 3 cases. So in one case, the entire thing is just 0, right? So we have 2x minus x squared is 0. And this happens when x is equal to 0 or 2. 0, 2. I'm just going to write it like that. And another case is when both of these are positive, because you want the difference to be positive, like so both of them can be positive. So 2x minus x squared has to be greater than 0. Or I'll just write that as x squared is less than 2x. Or x squared minus 2x is less than 0 actually, because that will make it easier to visualize. So the critical points of this inequality are 0 and 2. So when we draw out the number line, then we can visualize it as 0 and 2. So when you have less than 0, then you're kind of then you definitely have a positive, right? Because you're kind of dominating this entire, x squared dominates this entire thing, so this can't work. When you have greater than 2, obviously it's also positive. But when you have something in the middle, then you hit the sweet spot. So it's between 0 and 2 will work. But we also want x minus 3 to be greater than 0, so that means x is greater than 3. So in reality, we can't have anything here, so we can only have between these. We can have between these, and we can only have, so 1 will work, for example, right? Like if you have 1, then because it's 2 minus, actually wait, no, I'm looking at this wrong. It should be, if it's less than 0, if it's between 0 and 2, that won't work actually, because we know that 1 doesn't work in this case because 1 minus 2. Wait. Oh, okay. Never mind. Yeah, the way that we looked at it before was correct because, yeah. So these intervals have to be excluded, but we know that x has to be greater than 3. So I mean x minus 3 has to be greater than 0 in this case. I forgot what case we were analyzing. We're analyzing the case where both of these are positive. I accidentally wrote this inequality backwards, so I got confused. But x minus 3 is greater than 0, so x is greater than 3. That's kind of the deal that we have here. And if x is greater than 3, then we have to line this interval somewhere here, right? And obviously that won't work, so this is kind of an invalid case. So far we only have 0 and 2. Let's see if we can get more with the third case. I don't know why I switched color, but it doesn't really matter to me. Third case is when both are negative. So when both are negative, then that means x is less than 3. Oh wait. Also, by the way, we're looking at log n equals x, so that means that whatever we get for x, we have to convert it back in terms of n, and then when we look at the number of possible values for n. So right now we're dealing with everything logarithmically, kind of. So right now x is less than 3, and 2x minus x squared is less than 3. Is less than 0. So that means that x squared is greater than 2x, or x squared is less than, or x squared minus 2x is less than 0. So I'll just factor it, and then we can look at critical points. I should have just factored last time as well. It makes it easier to look at critical points. But you have 0 and you have 2, right? If you have less than 0, then this first one is negative, and this is obviously negative, so both of them will multiply to a positive, which is not what we want. So I'm just going to cross it off like this. Between 0 and 2, you have something like 1, right? And then 1 will be 1 times negative 1, which is less than 0, so that works. So between 0 and 2. Okay, wait, hold on. I'm doing this wrong again for some, or not again, but I'm doing this wrong. So it should be greater than. I don't know why I'm messing up so much. That's my bad. But yeah, this should be greater than. So actually, negative 1, for example, negative 1, for example, will not work because, negative 1 will work, for example. So this region of the inequality will work in this case. But the problem is we need x to be greater than or equal to 0, so that means that we can't consider that part of the inequality. And when we do between 0 and 2, for example 1, then that can't work because we're doing the thing where one of them is positive, one of them is negative, so that can't work. And when we do greater than 2, that works perfectly. Okay, interesting. But we also need x to be less than 3, so we need greater than 2 and less than 3. So we have this kind of situation here. So let me just draw out what we have in terms of our in terms of our set of values on the number line for x. So we know that x can be 0 from the first case. So there's a closed dot there. Maybe I should do this in white because it's easier to see. Zero, 2, there's a closed dot. I'll do this in blue. There's a closed dot at 0. Then at 2, we can do 2 with the first one. So there's a closed dot there as well. And we can go all the way up to 3, except at 3 there's a closed dot. At 3 there's an open dot, so we open this dot. And when we go back from the logarithmic scale into the regular scale, 0 becomes 1, which is fine. 2 becomes 100, and 3 becomes 1000, right? So the number of numbers between 100 and 1000, assuming that we skip one of them. So I mean the number of numbers from 100 to 1000 is 900 plus 1, which is 901, but then we get rid of the 3, or I mean the 1000 case, so we only have 900 numbers there, and then we do plus 1 for the 0 or the 1 in the regular scale, so we have 901, so that means that this should be E, I think. Wow, that problem was a little bit tricky. Okay. How many non-empty subsets B of this have the property that the number of numbers in, or the number of elements in B is equal to the least element of B? Number of elements in B is equal to the least. Okay. I guess I'll just draw out some cases and let's see. So my case will look like this. We're doing the min element that we use, and I'll just do the number of possible B's. So the minimum element, if it's 0, right, then we can't do the empty set, so and 0 isn't even in the empty set, so yeah, we can't do that. So when the minimum is 0, we have 0 cases. When we have 1, then we just have 1 case because we just have a set that has 1 in it. When we do 2, then how do we construct a set where the minimum is 2? And okay, so we have 2, and then we can choose from 3 to 12. 12 minus 3 plus 1 is 10. Wait, we can do 3. 12 minus 3 is 9 plus 1 is 10. Okay, yeah, so then when we have the minimum to be 3, then we can choose from 4 to 12. 4 to 12 is 9 elements, but we have to choose 2 of them, so we do 9 choose 2. This looks like it might be some sort of combinatorial identity, right? Because we can write 10 as 10 choose 1, and we can write 1 as 11 choose 0, and 0 doesn't matter. I don't know what the combinatorial identity would be though, because one of, like, if you look at the top, when you look at the top number in the binomial coefficient, then you know it's decreasing, but the bottom one's increasing. So I'm not really sure. I don't know. I'll just bash it out, I guess, for now. So 4 would be 8. The pattern is that the top number decreases and the bottom number increases. So 8 choose 3. Then 7 choose 4. 6 choose 5. And then we have 5 choose 6, which we know is 0. So everything past this point is 0. 8 choose, okay, so let's just calculate each of these. I'll do it in a different color. So 1, 10, 9 choose 2 is 9 times 8 divided by 2, which is 36. Then we have 8 times 7 times 6 over 6, which is 56. Then we have 7 times 6 times 5. Okay, wait, 7 times 6 times 5 times 4 over 4 factorial, which is 24, which is 6 times 4. So that's 35. And then we have 6 choose 5, which is 6, because it's just 6 choose 1. Okay, let's calculate this. So hopefully this is right. This is 17, and then we have 17 plus a bunch of annoying numbers. So 17, 36. I'll do this part a bit slower so we don't mess up the arithmetic. This is the sum. 6 plus 6 is 12 plus 7 is 19 plus 5 is 24. Then we have 5 plus 3 is 8 plus 3 is 11 plus 1 is 12 plus 2 is 1 plus it's 14, so 144. Okay. That means it's a D. Oh, and did we forget to write the problem number? I think we did. This is 8. Okay, number 9. What is the area of the region in the coordinate plane defined by this? Okay, so one thing I notice immediately is when you do the transformations x to negative x, which is the same thing as flipping it across the y-axis and y to negative y, then in both cases the equation, or I mean the inequality is preserved, right? So we only have to look at it in one quadrant, and then we can kind of just like flip it into all 4 quadrants. So in the first quadrant, what do we get? In the first quadrant, we can just remove the inside absolute values, and then we get x minus 1 absolute value plus y minus 1 absolute value is less than or equal to 1, and we know that's a diamond shape centered at 1, 1, like this. So in this, and then we flip the image into all 4 quadrants, so we just quadruple the area. We can just look at, so this is 1, 1. So this is 2 times 2, which is 4, divided by 2 is 2, so this is area 2, and then we flip it into all 4 quadrants, so that's 8B. Oh, and this is problem number 9. Okay, number 10. In an xy plane, circle of radius 4 is centered on the positive x-axis. Okay, I'll make this. And then it's tangent to the y-axis of the origin, so it looks like this. Something like this. I can't draw a circle, but 4, right? And then a circle radius 10 would, it's tangent to the x-axis at the origin, so it looks like this. Maybe something like this, right? This is 10. What is the slope of the line passing through the 2 points at which these circles intersect? So one of them is obviously the origin, and the other one is one we have to find. And then, yeah, I think that should be good. I think we can just bash this out. It can't be too bad. So x minus 4. The writing will be not fun though. X minus 4 squared plus y squared equals 4 squared. So x squared minus, so I'm just going to kind of simplify this in my head. So we get x squared plus y squared minus 8x on this side, and on the other side the two constants kind of cancel each other out, so we just get 0. And if you apply the same pattern to the other one, I think you can actually, okay, let me just make sure. So you got x squared plus y minus 10 squared equals 10 squared. The 10 squareds will cancel each other out, so it's the same pattern except with y. So x squared plus y squared minus 20y equals 0. So you can actually just like subtract these two equations, and that will give you 8x equals 20y, which means x over y is 8 over 20, which means it's 2/5. So it looks like E. Okay, what was this? I think I made another page by accident, but yeah, okay. Number 11, or actually now that I'm done with the first 10 and We finished in about 35 minutes. That's not too bad. It's a bit slower than I wanted to go though. Let's see what the rest of the problems look like. So we have isosceles trapezoid, maximum area, some binary operations. So Cyrus the frog jumps 2 units in one direction, then 2 more in another direction. What's the probability he lands less than 1 unit away from his starting position? Interesting. That's an interesting problem. Because if he jumps 2 in the same direction, then that's 4. But after he makes his first jump, then he can kind of... Wait, I might actually be able to do this right now. I'm not sure if this is a dumb idea, but this problem kind of intrigues me and we might have a bit of time. So let's see what I can do. 20... Okay, 2 units in one direction, right? So we can kind of fix the first jump. It doesn't really matter which direction it's in because it's arbitrary. And then from there we can use that as our pivot point. And we want to do less than 1 unit away from his starting position. So the starting position is actually over here, right? Less than 1 unit away would be this circle here. I don't know why I made that an open circle. This circle here. Can't draw stupid circles, but maybe I can do this and pretend like I have a circle. I have like a circle here, right? So we want to go within the circle, and we have, from this point we have 360 degrees of mobility. So is it not just this? It might actually just be this. So you just find the ratio of the area of this intersection to the entire thing, which is 4 pi. Oh, okay, yeah, this is exactly what you have to do, I think. So let me try to draw this a bit better. Probably bigger, actually. Okay, this is 1, this is 1. What we have here is some triangles. We know both of these are 1 actually, or all of these are 1. And you know, this is 2. This is 2. So 2, 2, 1. We have a 2, 2, 1 triangle, so that means that if you divide my brain is not processing this right now. A over sine A equals B over sine B equals C over sine C. We don't know any of these angles though. It's definitely one of the arcsine answers though. Or either arcsine or arctan. Which one is it? Which function do you have to use? Because you have arcsine and you have arctan. I'm pretty sure you have to use arcsine though, because you can just get like the thing from the law of sines. So okay, I'm pretty sure we just have to use arcsine. So, and the angles don't really work out because this is kind of like a weird kind of problem. So like basically like to make like a more rigorous argument here, right? You drop the perpendicular from here, and then you have 1/2, and then the 1/2 to 2 ratio is where the arcsine 1/4 comes from. So we're going to do E. That has to be the correct answer. Okay, cool. So far we have 11 done. We have to go back, but let's see if any of these other ones are easy to do. A real valued function f has the property that this. Okay, that's weird. When n standard 6-sided dice are rolled, the product of the numbers rolled can be any of 936 possible. Okay, this is an interesting one. 936. N standard 6-sided dice. This looks like a number theory problem, kind of. A number theory in combinatorics, because you look at the LC, or actually no, you don't look at LCM, you look at like how many factors of each of the primes will be involved. Actually, no, the product of the number is the product. Yeah, this looks like a weird one. The product of the numbers can be any. And then we have this weird LCM one. This looks like an LCM square, similar to the LCM triangle question from before, but okay, I don't know if I want to do these right now. I think we'll go back to them later if we have time, but we were at number 11, I think. Number 9, number 10. Okay, 11. We have an isosceles trapezoid that has legs of length 1 and one base twice as long as the other. So we have this situation. Legs of length 1, and this is x and this is 2x. What is the maximum area of this? Well, isosceles trapezoids are cyclic, but I don't think that's going to help us. I think what we have to do is we have to connect this up here, because this is like a classic trend in the AMC problems where they have like isosceles trapezoids like this. You have like the mid segment, and then you have like the base of a triangle, and you want to maximize this, right? So to maximize this, how do you do it? You know, this is 1 and this is 1 as well because it's a mid segment, and then you can do the sine triangle formula, which is, if this is theta, then the area of this is sine theta over 2, or the area of the trapezoid, right, is the area of the entire triangle, which is 2 times 2, which is 4, sine theta over 2, so 2 sine theta minus sine theta over 2. So 2 sine theta minus sine theta over 2. That means that in order to maximize that, we have to use theta equals 90 degrees. So 2 sine theta, I'm just going to call sine theta s for simplicity, minus s over 2. 2s is 4s over 2, minus s over 2 is 3s over 2. Okay, 3s over 2, and then s is sine. So in order to maximize sine, you have to make this 90 degrees, and I think that should be it. So we should just get D. Number 12. Define the binary operation. Okay, z is a complex number. We're going to make z a plus bi. So z x z would just be a squared plus b squared I. And this is problem 12 also. A squared plus b squared I equals z squared plus 10. So a z squared is a squared minus b squared plus 2abi, from what I can remember. Plus 40. What's the magnitude of z? The magnitude of z is square root of a squared plus b squared. So I think we just solve for them directly by equating the real and imaginary parts of this thing. So a squared cancels out. 40 minus b squared is the real part, and the other side is 0, so b has to be plus or minus square root of 40. It doesn't really matter which one we use because it's b squared, so let's use b equals square root of 40. And then on this, it's 2ab equals b squared. Or 2ab equals b squared, yeah, so that means b equals 2a. So a is square root of 40 over 2, which is square root of 10. So when we take the sums of these squared, then we get 40 plus 10, which is 50, and the square root of 50 is what? 5 times 5 times 2. So it's 2 root 5. Actually, no, I mean 5 root 2, which is e. Okay. Anyway, number 13. The rectangular box has edge lengths of this. The sum of lengths of all 12 edges is 13. The sum of the areas of all 6 faces is 11 over 2, and the volume of P is 1/2. What is the length of the longest interior diagonal connecting two vertices of... Okay. Well, what I think is that what we can do is we can do length of the longest interior diagonal is square root of a squared plus b squared plus c squared, essentially, right? And we know the sum of the lengths of all 12 diagonals are, the sum of the lengths of all 12 edges are sum of the lengths of all 12 edges is 13. And the sum of the areas of all 6 faces is 11 over 2. Okay, I think what we have to end up doing is we have to square this thing, because that's going to give us a bunch of information. Because we know 4 times this is 13 from the sum of the edge lengths, and then we know 2 times AB plus BC plus AC is 11 over 2, and then we know ABC is 1/2. So when we square this, then all we have to do really is we do A plus B plus C squared, and then all of the unwanted terms will be 2 times AB plus BC plus AC, which we already have actually, so we can just do this. So we can do this thing squared, which is 13 over 4 squared. The writing is not going well. 13 over 4 squared, and this is 11 over 2. Okay, this is 169 over 16. And then when you multiply this by 8, this is 88. So 169 minus 88 is 81. Okay, 81 over 16. And that, if you take the square root of 81 over 16, then you get 9 over 4. I think it's D. For how many ordered pairs A, B of integers does this have 3 distinct integer roots? This looks like Vieras to me, honestly, because we know AB, or I mean not AB, we should use like PQRS, I guess, if we're using the roots of this, but I mean, we should use PQR for looking at roots, probably, but we know PQR is -6 by Vieras. And this is problem 14. PQR is -6 by Vieras, and let's say, so what are the possibilities? We can have all of them are negative, so we have negative, 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 or we have exactly one is negative and the other 2 are positive. Or we can have, yeah, I'm pretty sure those are the only 2 possibilities. So when you have this, the only way you can have roots is this, and then you have 1, 1, 6. These are like the absolute values, so you put the signs in later. And then for the first case, all you can really do is make all of them negative, because if you use all of the negative ones on the second case, then you don't have unique roots. So there's one possibility here, and if you make 2 of them positive and 1 of them negative, that's the same as 3 choose 2 plus 1. 3 choose 2 is 3 plus 1 is 4. So 4 plus 1 is 5. So I think it should just be 5. I'm going with A. 15. Suppose A, B, C are positive integers such that A over 14 plus B over 15 equals C over 210. What of the following statements are necessarily true? Okay, well 14 times 15 is 210, so I'm pretty sure this will just rearrange nicely into this 15A plus 14B equals C. And then, okay, yeah, exactly. Now I'm just reading the different statements, right? If GCD A14 equals 1, or GCD, this is getting cut off a little. If GCD A14 is 1, or GCD B15 is 1, or both, then GCD C210 is 1. Okay, GCD A14 is 1, so that means A is relatively prime to 14. So if A is relatively prime to 14, and B is relatively prime to 15, then the GCD 14 is 2 times 7, 15 is 3 times 5, so their primes are all different. And that's interesting. But then you have okay, or I think you need an and actually. You can't have or, you need and, because if you just have or, then the other, then you can still possibly factor out a 210. Because when you factor out a 210, then C has to be divisible by 210. So this is definitely not true. So I is wrong. If GCD C210 equals 1, then this equals 1 or this equals 1 or both. Yeah, it's kind of the contrapositive, or I don't know if contrapositive is the right word, but it's like the opposite of the first one, and the opposite will work because if the GCD is 1, then the factors can't be shared, so 2 is definitely true. 3, it equals 1, and if and only if both of them are 1, that's what I've been saying, so 3 is true for sure. So that means that it's E, only I, and I are true on, this is 15. 16, in Coinland there are 3 types of coins, each worth 6, 10, and 15. What is the sum of the digits of the maximum amount of money that is possible to have? So this looks like a modification of Chicken McNugget theorem, actually. So let's see what we can do here. 6x plus 10y plus 15z. Can we split 10y into something nice, like 3 plus 7, 4 plus 6, 5, 4 plus 6, 5 plus, maybe we can split them. Oh, you know what? I'm probably just going to try out different cases here. 15, we can definitely make 16, we can definitely make 17. 16 is 6 plus 10, 17. 17, can you make it? I don't think you can make 17. Okay, that's not good. 18. Actually, no, this will work. Let's not do it like this. Let's say this is equal to let's say this is equal to n, right? If we do n I think I'll have to skip. I'll have to skip this. Triangle ABC has side lengths in an arithmetic progression. The smallest side has length 6. If the triangle has angle, okay, this looks pretty free to me. This is just 6 plus x, 6 plus 2x. And you know the triangle is an angle of 120, so that has to be the opposite, the largest side. So this is just a law of cosines. So a squared plus b squared plus 2ab, so 12 times 6 plus x. Sine 120, which I think is a negative 1/2, equals 6 plus 2x squared. And we solve this. 6 squared is 36. Right. Sine 120 is negative 1/2. So this is a negative 6. Writing on this is not it at all. 36 plus x squared. I'm just going to write on a separate piece of paper. I don't think I can deal with writing on this, but You get the idea, you just solve the equation. Okay. Okay, so I'm getting that x equals 10. So if x equals 10, then we have 6 times 16 times the sine. Or also, yeah, by the way, this was supposed to be cosine, not sine. That's me miswriting this, but yeah. The sine of 120 will be root 3 over 2, yeah. So it will be 6 times 10 times root 3 over 2 over 2. So it will be 15 root 3, I think so. And 17. Let's try 19. It looks short. Each of 2023 balls is placed into one of 3 bins. Which of the following is closest to the probability that each of the bins will contain an odd number of balls? So, you have 2023 balls, 3 bins, and it looks like the stars and bars kind of thing, right? Let's say you have 2023 balls. You want all of them to contain an odd number of balls, so how can you place your dividers to do that? Well, the first divider has to go into exactly half of the positions, or I mean, I don't know if it's half. I guess it should be pretty much half. So when you have like 3, right? Or let's say you have 5 to make it a bit better. To do 5, you can place your first divider here. You can place your first divider here. So there are 2 of 4 spots that you can place your first divider. And then after that, like after you place your first divider, you have another, you kind of reduce it to a sub-problem where you have another odd number of balls, or like an even number of balls approximately. So the probability of placing the first divider to get an odd number of balls seems like 1/2, and then for the next divider it should be 1/2 as well, I'm pretty sure, because you just have like another sub-problem, and like half of the spots will be spots where if you place the divider then you get an odd number of balls, because it's like the same as the problem above it. So I think it should just be half times a half, and then the third, you don't need to worry about the third thing because there are only 2 dividers you have to place. The third bin will automatically be taken care of, so I'm pretty sure it's just E. Okay. What else here looks approachable? I think I'll actually go back to that one problem. The Coinlandia one, number 16. Where is it? I think it's here somewhere. Yeah, it's here. I'll title this number 16. We only have 5 minutes left. In Coinland, there are 3 types of coins. Okay, so this looks like a modular arithmetic problem to me, but there is going to be a lot of casework here, is what I think. So that's why I don't want to do this right now, but everything else looks like it's going to take kind of an annoying amount of time as well. I wasn't able to go as fast on this because like I had to write out things on without like a stylus or anything like that, like without an Apple Pencil, without a stylus, so I'm kind of going a bit slow. But okay, I'll just do this, and then if we can't figure it out in the amount of time, then it's whatever. But I think the move here will be to be going in mod like 6, because then like, or any mod, it shouldn't really matter, but like if you do mod 6, then at least you'll be able to do some reduction here. So mod 6, what happens to y? Mod 6, y becomes 4y, and 15, this becomes 3z. So mod 6, this goes away, and this is congruent to n mod 6, right? And then you know from the chicken McNugget theorem that it's mn minus m minus n, so 4 times 3 is 12 minus m minus n. So minus 3 minus 4. 12 minus 7 is 5. Okay, so the highest value in mod 6 should be the highest value in mod 6 should be 5. So the answer has to be 5 mod 6, essentially. And then when you look at mod 10, right? Actually, no, that won't work, because I was thinking of using the Chinese remainder theorem to figure this out, but I think, okay, so we know the answer has to be 4 mod 5. I mean, sorry, not even mod 5, the answer has to be 5 mod 6. The answer has to be 5 mod 6, and can we make some deduction about what that means about what has to be mod 9? 5 mod 6 can be what mod 9? Because, so 5 mod 6 can be 5 and then 11, and then you add 6 again, so 17. Mod 9, this is 5, 2. Mod 9, 5, 2. So it's either 2 or 5 mod 9. So that means that it's either 11 or yeah, it has to be 11, because you can't have, like, nothing else here works, because you can't have 2 or 5 mod 9 from anything else here. Everything else is a mod 9, 1 mod 9, 7 mod 9, 0 mod 9. So I think that means that we can actually just do, so I think it's actually just 11. Okay, that was kind of a clutch solve there. Everything else here looks like it's gonna take too much time for right now. I'll definitely go over these problems later at the end. I don't know how many we solved here, but yeah, I think we solved around 18 problems. I don't know how many of them I'll have right, but I think I'm pretty confident for all of them. I didn't make any guesses or anything, so I should be okay. That's pretty much it. We don't care about the timer anymore. I won't really solve anything else, but okay. I guess we can now just like start checking these to see how I did. I don't know. Hopefully I did okay. Problem 1. Actually, can we just go to the solutions? Or I mean the answer key. Is there an answer key here? Can you just click this? Okay. Problem 1 is C. So for answers, is there a separate color I can use? I'll just use red. So C is indeed correct. And then we have B, D, C, C. Oh shoot, okay, we got this one wrong. Really? How did we... I'm actually really curious what happened there. 6. What was the correct answer? 5? Wait. Wait, am I reading this wrong? Hold on. Why is the answer key different from the solutions? Okay. Now I'm confused. What should I trust? Let's just go back and try to regrade these then, because I really don't know what's going on anymore. I'll just go off the solutions, I guess, because at least the solutions have like justifications and they have like multiple solutions, so it can't be as weird as the answer key, I guess. Should be correct. Let's take it back. 1 was C, good. 2 was... Oh wait, can I use... I'll just go back and go to each one. 2 was B. Bruh, okay. 2 was B. 3 was D. Was it? Yeah. Cool. 4. Was C. Actually, maybe it is faster to use these. Oh, this is 10B, it should be 12B. 5 was 4, okay, so C. 6. We already saw 6 was D from... Okay, 6 is D, right, yeah, cool. 7. Seven was E, cool. 8. Eight was D, right? Yeah, okay. 9. I'm actually curious, was there an identity that they used to do this or no? No, I don't see one. Oh wait, in general when the number is not 13, the answer is Fibonacci n minus 1. I wonder why that works. I don't know. Maybe there's a combinatorial identity or something, but that's interesting. Problem 9. Okay, good, it's B. Problem 10. I put E. Let's see what it was. Okay, it was E. Problem. Oh, okay. I did problem 20 next, but we'll go back to problem 20, I guess. Let's do problem 11 first. Problem 11, I put D. That's correct. Problem 12. Problem 12, I put E. That's correct. So far, none wrong. That's actually that's pretty decent. I guess I was working a little bit slower than usual, since I only solved around. But I don't know if that was because of my, because of I had to write it and kind of like walk through it, like verbally, or if I was just working slower than usual. But it's good. The accuracy is good. Okay, this is a D. Problem 14. I hate the way they make these navigation things. Okay, this is 5A. Okay. Problem 15. Problem 15. Okay, good. E. No mistakes so far. Not bad. Problem 16. Problem 16 is indeed D. Okay, look at the number. Look at the amount of casework they did for this. I'm glad I found the, I just found the modular solution to this, but the amount of casework is crazy. 17. Okay, 17 is E. Cool. 18. Wait, did I do 18 or no? I don't think I did 18. Yeah, I didn't do 18. I'm not even reading the solution right now. I get 19. Okay, yeah. I think this is pretty much, yeah, half times half is pretty much what I did. But yeah, 19E. Okay, and then we did 20 as well, right? I think. Let's do 20 and see. Okay, I was the arc sign one. I was correct. So okay, I solved, how many problems is this? I'm pretty sure it's 18. I'll just count them up real quick, but no mistakes. That's pretty nice. Whereas, I'll just count it up. So from the beginning, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, I mean 10, 11, 12, 13, 14, 15, 16, 17, 18, oh, 19. Really? Wait, I want to make sure that I did 19. I thought I was under the impression I only had 18. Let me check. How do you go back to the main menu? I have to use this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay, I did do 19. Okay, so what is that? Plus 1.5 times 6. 1.5 times 6 is 9 points. Yeah, and then 19 times 6 is 114, I think. Wait. That is, okay, so I got a 123. That's not too bad, honestly. Okay, so I guess that pretty much concludes this. I guess now I'll give my thoughts on the test really quickly in terms of what I thought of the quality and probably like just the overall vibe of the test. I thought the quality, it wasn't the best, honestly. I think there were some questions which felt very formulaic to me, like let's see if I can go through them. Like 3 seemed very formulaic to me, like what's the point of having a problem where like the only thing you have to know in 3 is just the fact that like the radius of the radius of the circumcircle is 1/2 of the radius, I mean 1/2 of the like hypotenuse. That's all you have to know. But if you know that, then the problem's like nothing. The problem's like a number 1 or something. But if you don't know that question, or if you don't know that property, then the problem's pretty much impossible. And I think like the AMC and like other tests should just avoid questions like this. We call them one-trick ponies sometimes in like the problem writing communities. And it's just like, it's not good. It's just like a problem that involves one trick, and if you know the trick, then you know the problem, and that's pretty much it. Like it just tests if you know that one trick. There's no point. And then yeah, question number 4, I didn't really see a point to. Like I guess it's testing if you can convert units or something. I don't know. Other than that, it's multiplication. Problem 5 I thought was reasonable. I guess like there was some casework involved. It wasn't really the best. Problem 6 felt kind of like an SAT math problem, because I know they test like the multiplicity of roots trick to see if the thing goes through or bounces off. I don't think there's really a point of putting it here, but not the worst problem, not my favorite either. Problem 7 I liked. I thought it was decent. You had to do some casework and some inequality solving. Yeah, I don't know. The quality wasn't it. Problem 8, I think it was a good problem, but I think it could have been made better if they used some sort of combinatorial identity that was more recognizable, like I don't know, Pascal's identity or Vandermonde or something. Like But like in that case, then maybe it couldn't be a problem. Maybe it could be like a problem number 12 or something if it uses the identity. Problem number 9 was another one of those things where you either don't know the trick and you spend like endless amounts of time graphing. Like I guess it was a decent problem in the sense that like if you recognize symmetry across the x and y axes, then you only have to worry about the first quadrant, and then you can kind of just like sketch out the rhombus, and then it gets fine after that. But I don't know. If you don't know, like if you know the fact that it's a rhombus, like it's a very common thing that's tested on pretty much all AMC 10s that involve this kind of problem in some form, then you're chilling. But otherwise, like you have to worry about figuring that out. So it also kind of had that one trick pony feel a little bit. It didn't seem like very genuine problem solving to me, but yeah. Then problem 10, I don't know, it seemed kind of pointless to me. You just solve a system of equations and you don't really, there's no point. Problem 11, this was the mid-segment problem. I thought it was okay, I guess. It wasn't really, yeah, it wasn't the best either in my opinion in terms of quality. Problem 12 was okay, I guess. It was equating. Problem 12 is just like you put it in, like you don't even, like the binary operation thing they have here is just decoration. You just put the thing in, you solve the equation, you equate the imaginary parts. Like, yeah. And problem 13, I feel like I've seen this before, like a lot. It's kind of overused as a concept. The fact that you square a plus b plus c and then you get rid of all of the pairwise products, but yeah, it wasn't the worst. It was a repeated concept. Problem 14, it was just you just recognize the Vietas and you do some casework. Like there was no point in my opinion. Problem 15 was somewhat decent in terms of you had to recognize divisibility, or like divisibility and then like how the GCD and everything relates to that. So I thought problem 15 was honestly one of the better problems on the test in my opinion. Problem 16 I actually liked. It's an extension of the chicken McNugget theorem, which works only for 2 numbers, but you extend it out to like 3 numbers. And yeah, problem 17 was just law of cosines followed by like sine triangle formula bash, which seemed kind of pointless to me. Again, problem 19 was my favorite problem on the test, honestly. I don't think it deserved to be, or I don't know if it deserved to be a number 19 because it was more or less just like a modification of stars and bars, and it's just 1/2 times 1/2 if you see the idea. You just put the divider in first and then you put the second divider, but it was still one of the highest quality problems on the test in my opinion, at least out of the ones that I attempted, because I don't know, like there was some problem solving and some creativity involved. Problem 20 again, not a bad problem. Not the best problem either, but the first part of this problem is just you draw the diagram and you look at the area, and then you realize it's just like a geometry problem at the end of the day, and then you find the area and you do the geometric probability thing. The other things I don't think I attempted. Problem 24 looks like a repeat of that one problem, and I don't know if it was back in 2016 or something, where they had like in the official AOP solution, I remember they basically just had like a triangle, and then they looked at they kind of just organized, like they made a triangle for each divisor, I think, and then they organized the exponents. I thought it was a pretty cool solution. I'm pretty sure you can do the exact same thing on this, so it seems kind of like a repeat problem. Like I don't think there's any difference actually between this and that. Maybe there's some like minor difference. 25, I haven't attempted this. It doesn't seem like it would be too bad. You'd probably use like some sort of quadrilateral thing, or it's like a pentagon actually, so you'd probably use like, I don't know, some geometry skills in breaking down the areas. Yeah, I'll look through the other problems. I'm not sure if I'll do them on screen or not. The whole point of this was just to kind of do a live solve. I think it went decently. It could have went better, but it is what it is. But yeah, I think that's pretty much it in terms of my review of the test. So not the highest quality test at all in my opinion, but it was kind of like one of those tests. If you know the tricks, then you can kind of get through the test. And then in terms of my cutoff predictions, I think with the way the AMC is now, where they're kind of more lenient, I think if you get at least a 90 on this test, I'm pretty sure that you'll qualify for AIME. Like, don't take my word for it, like 100% probability, but I'm pretty sure like there's a 90% chance if you get a 90 you're going to qualify. If you get 100 you're definitely qualifying. Like, there's no way that the cutoff for this is going to be over 100, because there are too many like random tricks that you had to know. It could potentially be less as well. It could be maybe 84 or something. I don't know. Like, you can look at the historical data and see how it kind of lines up with other tests. My personal conservative cutoff prediction is around 90 for this. And yeah, I think if you get around the score that I did, like the score that I put off here, which was I think 123, then you should also be fine for USAMO probably if you do relatively well in the AIME. And yeah, other than that, I think that's pretty much it.